We are on the final set of notes for this unit. We are looking at graphing and organizing data. One of the things that scientists use to organize their observations are called data tables. If you use a computer to generate your data tables, we often refer to them as spreadsheets because you can manipulate within that software to do other things. So data tables or spreadsheets contain both the manipulated variable and the responding variable, so what you're controlling and the outcome that you are observing. So it organizes our observations and it allows for ease for analysis. So we can see trends in data sometimes just by looking at it, or like I said, if we did a spreadsheet, we can highlight areas of it and have it plot or graph that information so we can get a nice visual of it. One of the ways that we like to see data is in a line graph. So usually the manipulated variable is on the x-axis, so that's going horizontal across the bottom, and the responding variable is on the y-axis, and so that's the vertical axis going up and down on the left. Keep in mind I am using the term usually. Sometimes when we collect data, we're not thinking manipulated and responding like density. Which one do you really do first, mass or volume? So who depends on who. But the slope, which relates the two values, could dictate which axis is which, because in density the formula is mass over volume. So slope in this case, we have rise over run, or the change in y over the change of x. So if the formula is mass over volume, that's telling us that y needs to be the mass and x needs to be the volume. When we look at a graph, we do what's called a linear regression. That's a function you can do in Excel, so you don't have to calculate it. And if you're doing it by hand, it would be called a best fit line, because you're just hand drawing it and you're trying to do your best to do it. This is, you see that there is the y equals mx plus b. Now in math class, you're used to having that formula and then calculating y or x. But in science, you don't have that formula. That's what you're trying to generate. So you're collecting a lot of data points and then doing that linear regression to determine y equals mx plus b. Whether we have the slope of the line or not, sometimes it's just easier not to calculate. We draw the best fit line and we can interpolate the data. We can find information within the set of data that we collected. So in this example, we see we started at 5 and we collected data up to like 25. There's really no point there for 15. So we can mentally or physically draw a line from 15 on the x-axis and then go to the left and see where it hits on the y-axis. So that's interpolating data. You're finding data within a given set of data points. You didn't actually collect that particular point. If we can look inside data, we can look outside data sets. So extrapolate. We're obtaining data outside the data points we collected. So we only collected data from 5 to 25, but we can extend our line and we can determine what 30 would be. So we're predicting what that is. We're not really sure. I mean, we could keep collecting data points and the graph can suddenly drop. We don't know. So we're extrapolating based on the data we have and completely predicting those areas that we don't have data for. We didn't get that far, or we didn't start at 0. And the extrapolation on this graph is shown in the red, so those are the areas that's outside the actual points we collected. Some of the things we think about is being proportional. So when you can divide a number by another quantity, you always get the same number or a constant. So when things are proportional or direct proportional, as one increases, the other decreases, and vice versa. So you always get a straight line for the graph. It's linear, and it passes through the origin. Now sometimes we know y equals mx plus b. It doesn't always pass through the origin, meaning 0, but the origin being your first point. Inverse proportions are when we're multiplying a quantity by another quantity and we get the same number as constant. So as one increases, the other decreases. The graph will be a hyperbola or a curve. So it's not always this beautiful straight flat line with a slope. You actually kind of have to connect the dots a little bit. One of our other types of graphs, we don't use them too often for our data in our labs, but we can, and it's called a bar graph. I believe you could also call it a histogram, depending on what you're doing with it. So the bar graphs are used to still compare data, and when we're doing that, we often involve a qualitative grouping and counting. So we could, and this example is picking up trash on the beach, we could classify all the different types of things we picked up and count them. If we think about the census, they're collecting data per year, and then they show how many people had raises that year or their income had increased that year. So the year, even though it's a number, it's really a group. It's representing a large group. We also have pie charts, and this is our last slide. So pie charts, they show how a part relates to a whole. So you have a slice of pie, just part of the pie. Another way we think about this is percentages. So we can talk about all the different types of movies out there, and for this given set of data, say 27% of the movies made this year were comedy and 18% were action. We have no idea how many movies were actually made this year, but we have the percent. So we have part of it to a whole, we have the percent. This is just like test scores. So how many do you have right out of the total number? So you're comparing the part right to the whole, the actual test questions.